Ionisation and excitation. This simple animation will look at ionisation and excitation using the very simple model of the atom you'll be familiar with, of a nucleus in the centre being orbited by an electron. This electron, shown in a different colour just for clarity, will collide with this electron, passing on sufficient energy for this electron to escape from its nucleus. The electron is orbiting, the other electron comes in, collides with it, giving it sufficient energy to escape. This is now a charged particle, or an ion, so that was ionisation. The electron has been given its ionisation energy due to the collision. Now to look at excitation using the same simple orbiting electron model. In this case, the orbiting electron isn't given sufficient energy to escape, but goes to a higher orbital, or a higher energy level as it's called. It's been excited to a higher energy level. This is a simple explanation of excitation. We're going to look at the energy levels available to an electron in an atom of hydrogen. Hydrogen, having just one proton in the nucleus and one electron, is by far the simplest of the atoms and so the easiest to analyse. It was found that the electrons could only have certain specific energy levels. The lowest state, here at minus 13.6 electron volts, we call n equals 1, or the ground state. You can consider that the most stable state, rather like if you had a ball and a series of shelves you could put it on. This would be with the ball on the ground. Next we have n equals 2, just up here, n equals 3, n equals 4. You'll see the energy levels are getting closer, and they get closer and closer still, until they're so close that they're indistinguishable, and beyond this we have what is ionisation. The electron, if it was given more than this energy, would be free. The energy levels are negative because we take the position of a free electron up here as being zero energy. If it's trapped within an atom, it has less than zero energy. Another way to think of it is the energy that would be required to free up the electron. So for example, from the ground state, we would need to give the electron at least 13.6 electron volts to allow it to escape from the atom. So therefore, at the moment, it effectively has minus 13.6 electron volts. We give it that energy, and it would then have 0 electron volts and be free. Now we have an electron in the ground state. It could be given energy by collision with another electron, as shown in the previous animations, or it could absorb a photon. Here is a photon, and if it's absorbed by the electron can move up to, for instance, the n equals 2 energy level. If the photon didn't have sufficient energy for it to get to the n equals 2 energy level, it couldn't, for example, end up here. It has to be either at n equals 1, n equals 2, n equals 3, and so on. It is only allowed these specific energy levels. So absorbing a higher energy photon could send it to n equals 3, an even higher energy photon to n equals 4, and so on. If there was sufficient energy, as here, the electron becomes free. We have had ionisation. But just as a ball on a high shelf is not stable and will probably fall off at some point, an electron in a higher energy level, for instance here an electron which has been raised to the n equals 4 energy level, is not stable, and very soon we'll want to go back down to a lower energy level, in this case the ground state, and in so doing it must lose its energy in the form of a photon. It doesn't necessarily have to drop straight to the n equals 1 energy level. For example, it could go down to the n equals 3 energy level, emitting a photon, then down to the n equals 2 energy level, emitting another photon, and finally down to the n equals 1 or ground state, emitting a further photon. Other combinations are also possible. For example, it could go from n equals 4 to n equals 2, and then down to n equals 1, and so on. If we pass the light emitted from hydrogen gas through a diffraction grating, this is what we see: distinct lines with distinct wavelengths. For example, a red line here with a wavelength of 656 nanometers, a green line at 486 nanometers, and so on. How these lines come about is from different energy level drops. So here we have our energy level diagram again, with some details missing for clarity. The red line here equates to a drop from n equals 3 to n equals 2. The green line from n equals 4 to n equals 2, and so on. These lines are the visible lines given off by hydrogen. They're called the Balmer series because it was a man called Balmer who discovered them. There is another series of lines called the Lyman series, which is drops down to the n equals 1 energy level. But these aren't visible, they're in the ultraviolet part of the spectrum. Another series of lines in the infrared drop down to the n equals 3 line. They're called the Paschen series. So let's look at this red line at 656 nanometers in a little bit more detail. It's the drop from n equals 3 to n equals 2. On this diagram we can show it with this arrow from n equals 3 to n equals 2. Now the n equals 3 energy level is at minus 1.5 electron volts. N equals 2 at minus 3.4 electron volts. So the photon energy is going to be the difference between the amount of energy it has here and the amount of energy it has here, which is minus 1.5 electron volts minus 3.4 electron volts, which gives the photon an energy of 1.9 electron volts. To get from electron volts to joules, as we must do, we multiply electron volts by the charge on the electron, 1.6 times 10 to the minus 19, and that gives us an energy of the photon of 3.04 times 10 to the minus 19 joules. We also know that photon energy E is given by hf, where h is Planck's constant, f is the frequency. Or as wave speed equals frequency times wavelength, we can write this as E equals hc over lambda, where h is Planck's constant, c the speed of light in a vacuum, and now lambda the wavelength. Rearranging to find the wavelength, we find that lambda equals hc over the photon energy E. Putting the numbers in, this is Planck's constant, 6.63 times 10 to the minus 34 joule seconds, times the speed of light in a vacuum of 3 times 10 to the 8 meters per second, divided by the photon energy found previously of 3.04 times 10 to the minus 19 joules. This gives a wavelength of 654 nanometers. Previously we showed the line to be 656 nanometers. The difference is just down to rounding errors in the numbers we've used. In more general terms, we can write that the energy of the photon, E1 minus E2, the energy of the first energy level minus the energy of the energy level it drops to, is given by Planck's constant times the frequency, or alternatively Planck's constant times the speed of light in a vacuum divided by the wavelength of the light.